When did you first fall in love with robotics?
Well, I was always a builder from a young age. I was lucky. My father was a frustrated engineer, and by that I mean he wanted to be an aerospace engineer, but his mom from the old country thought that that would be like a grease monkey, and so she said no. So he became an accountant. But the result of that was our basement was always full of tools and equipment and electronics. And from a young age, I would watch him assembling a kit, an ICO kit or something like that. I still have a couple of his old ICO kits. And but it was really during graduate school when I followed a professor back from class. It was Bertolt Horn at MIT, and I was taking an interim class. It's IAP, Independent Activities Period.
Mm-hmm.
And I followed him back to his lab, and on the table was a Vicarm robot arm taken apart in probably 1,000 pieces. And when I saw that, from that day on, I was a roboticist.
Do you remember the year?
1974.
1974. So there's just this arm in pieces.
Yeah.
And you saw the pieces, and you saw in your vision the arm when it's put back together and the possibilities that holds.
Somehow it spurred my imagination. I was in the Brain and Cognitive Sciences department as a graduate student doing neurophysiology. I'd been an electrical engineer as an undergrad at Northeastern. And the neurophysiology wasn't really working for me. It wasn't conceptual enough. I couldn't see really how by looking at single neurons you were going to get to a place where you could understand, control systems or thought or anything like that. And, the AI lab was always an appealing, this was before CSAIL, right? This was in the 70s. So the AI lab was always an appealing idea. And so when I went back to the AI lab with, following him, and I saw the arm, I just thought, this is it.
It's so interesting. The tension between the BCS, Brain and Cognitive Science approach to understanding intelligence, and the robotics approach to understanding intelligence.
Well, BCS is now morphed a bit, right? They have the Center for Brains, Minds, and Machines, which is trying to bridge that gap. And even when I was there, David Marr was in the AI lab. David Marr had models of the brain that were appealing both to biologists, but also to computer people. So he was a visitor in the AI lab at the time. And I guess he became full-time there. So that was the first time a bridge was made between those two groups. Then the bridge kind of went away, and then there was another time in the 80s. And then recently, the last 5 or so years, there's been a stronger connection.
You said you were always kind of a builder. What stands out to you in memory of a thing you've built? Maybe a trivial thing that just kind of like inspired you in the possibilities that this direction of work might hold.
I mean, we were just doing gadgets when we were kids.
Yes.
I have a friend, we were taking, I don't know if everybody remembers, but fluorescent lights had this little aluminum cylinder. I can't even remember what it's called now, that you needed a starter, I think it was. And we would take those apart, fill them with match heads, put a tail on it, and make it into little rockets.
So it wasn't always about function. It was,
well, rocket was pretty much
I guess that is pretty functional.
Yeah.
But yeah, I guess that is a question. How much was it about function versus just creating something cool?
I think it's still a balance between those two. There was a time, though, when I guess I was probably already a professor or maybe late in graduate school, when I thought that function was everything, and that, mobility, dexterity, perception, and intelligence, those are sort of the key functionalities for robotics, that that's what mattered and nothing else mattered. And I even had kind of this Platonic ideal that a robot, if you just looked at a robot and it wasn't doing anything, it would look like a pile of junk, which a lot of my robots looked like in those days. But then when it started moving, you'd get the idea that it had some kind of life or some kind of interest in its movement. And I think we purposely even designed the machines not worrying about the aesthetics of the structure itself. But then it turns out that the aesthetics of the thing itself add and combine with the lifelike things that the robots can do. But the heart of it is making them do things that are interesting.
So one of the things that underlies a lot of your work is that the robots you create, the systems you have created for over 40 years now, have a kind of, they're not cautious. So a lot of robots that people know about move about this world very cautiously, carefully, very afraid of the world. A lot of the robots you built, especially in the early days, were very aggressive, under-actuated. They're hopping. They're they're wild, moving quickly. So what is there a philosophy underlying that?
Well, let me tell you about how I got started on legs at all. When I was still a graduate student, I went to a conference. It was a biological legged locomotion conference, and I think it was in Philadelphia. So it was all biomechanics people, researchers who would look at muscle and maybe neurons and things like that. They weren't so much computational people, but they were more biomechanics. And maybe there were 1,000 people there. And I went to a talk. One of the talks, all the talks were about the body of either animals or people and respiration, things like that. But one talk was by a robotics guy, and he showed a 6-legged robot that walked very slowly. It always had at least 3 feet on the ground, so it worked like a table or a chair with tripod stability, and it moved really slowly. And I just looked at that and said, "Wow, that's wrong. That's not anything like how people and animals work, because we bounce and fly. We have to predict what's going to happen in order to keep our balance when we're taking a running step or something like that. We use the springiness in our legs, our muscles and our tendons and things like that as part of the story. The energy circulates. We don't just throw it away every time. So I'm not sure I understood all that when I first saw it, but I definitely got inspired to say, let's try the opposite. And I didn't have a clue as to how to make a hopping robot work. Not balanced in 3D. In fact, when I started, it was all just about the energy of bouncing, and I was going to have a springy thing in the leg and some actuator so that you could get an energy regime going of bouncing. And the idea that balance was an important part of it didn't come until a little later. And then, I made the one-legged, the pogo stick robots. Now I think that we need to do that in manipulation. If you look at robot manipulation, a community has been working on it for 50 years. We're nowhere near human levels of manipulation. I mean, we can, it's come along, but I think it's all too safe. And I think trying to break out of that safety thing of static grasping, if you look at a lot of work that goes on, it's about the geometry of the part, and then you figure out how to move your hand so that you can position it with respect to that, and then you grasp it carefully, and then you move it. Well, that's not anything like how people and animals work. We juggle in our hands, we hold multiple objects and can sort them. So now, to be fair, being more aggressive is going to mean things aren't going to work very well for a while. So it's a longer term approach to the problem. But that's just theory now. Maybe that won't pay off, but that's sort of how I'm trying to think about it, trying to encourage our group to go at it.
Well, yeah, I mean, we'll talk about what it means to what is the actual thing we're trying to optimize for a robot. Sometimes, especially with human robot interaction, maybe flaws is a good thing. Perfection is not necessarily the right thing to be chasing. Just like you said, maybe being good at fumbling an object, being good at fumbling might be the right thing to optimize versus perfect modeling of the object and perfect movement of the arm to grasp that object. Because maybe perfection is not supposed to exist in the real world.
I don't know if you know my friend Matt Mason, who is the director of the Robotics Institute at Carnegie Mellon, and we go back to graduate school together. But he analyzed a movie of Julia Childs doing a cooking thing. And she did, I think he said something like there were 40 different ways that she handled a thing, and none of them was grasping. She would nudge, roll, flatten with her, knife, things like that. And none of them was grasping.
So, okay, let's go back to the early days. First of all,
Sure.
you've created and led the leg lab, the legendary leg lab at MIT. So what was that first hopping robot?
But first of all, the leg lab actually started at Carnegie Mellon.
Carnegie Mellon.
So I was a professor there starting in 1980 to about 1986. And so that's where the first hopping machines were built, starting, I guess we got the first one working in about 1982, something like that. That was a simplified one. Then we got a three-dimensional one in 1983. The quadruped that we built at the Leg Lab, the first version, was built in about 1984-5 and really only got going about 86 or so. And it took years of development to get it to really.
Let's just pause here. For people who don't know, I'm talking to Marc Raibert, founder of Boston Dynamics. But before that, you were a professor developing some of the most incredible robots for 15 years. And before that, of course, a grad student and all that. So you've been doing this for a really long time. So you like skipped over this, but like go to the first hopping robot. There's videos of some of this. I mean, these are incredible robots. So you talked about the very first step was to get a thing hopping up and down.
Right.
And then you realized, well, balancing is a thing you should care about, and it's actually a solvable problem. So can you just go through how to create that robot? What was involved in creating that robot?
Well, I'm going to start on not the technical side, but I guess we could call it the motivational side or
Sure.
the funding side. So before Carnegie Mellon, I was actually at JPL, at the Jet Propulsion Lab, for 3 years. And while I was there, I connected up with Ivan Sutherland, who is sometimes regarded as the father of computer graphics because of work he did both at MIT and then University of Utah and Evans and Sutherland. Anyway, I got to know him. And at one point he said he encouraged me to do some kind of project at Caltech, even though I was at JPL. You know, those are kind of related institutions. And so I thought about it, and I made up a list of 3 possible projects. And I purposely made the top one and the bottom one really boring sounding. And in the middle, I put a pogo stick robot. And when he looked at it, you know, Ivan is a brilliant, brilliant guy, brilliant engineer, and real cultivator of people. He looked at it and knew right away what the thing that was worth doing. And so he had an endowed share. So he had about $3,000 that he gave me to build the first model, which I went to the shop and with my own hands kind of made a first model, which didn't work and was just, a beginning shot at it. And Ivan and I took that to Washington. And in those days, you could just walk into DARPA and walk down the hallway and see who's there.
Yeah.
And Ivan, who had been there in his previous life. And so we walked around and we looked in the offices. Of course, I didn't know anything. You know, I was basically a kid, but Ivan knew his way around. And we found Craig Fields in his office. Craig later became the director of DARPA, but in those days, he was a program manager. And so we went in. I had a little Samsonite suitcase, which we opened, and it had just the skeleton of this one-legged hopping robot. And we showed it to him. And you could almost see the drool going down his chin
of
excitement. And he sent me $250,000. He said, okay, I want to fund this. And I was between institutions. I was just about to leave JPL, and I hadn't decided yet where I was going next. And then when I landed at CMU, he sent $250,000, which in 1980 was a lot of research money.
Did you see the possibility of where this is going? Why this is an important problem?
No.
The balancing, I mean, it's legged. It has to do with legged locomotion. I mean, it has to do with all these problems that the human body solves when we're walking, for example. Like all the fundamentals are there.
Yeah. I mean, I think that was the motivation, to try and get more at the fundamentals of how animals work. But the idea that it would result in, machines that were anything like practical, like we're making now, that wasn't anywhere in my head. No. As an academic, I was mostly just trying to do the next thing, make some progress, impress my colleagues if I could.
And have fun. Pogo stick robot.
Pogo stick robot.
So what was on the technical side? What are some of the challenges of getting to the point where we saw, like in the video, the pogo stick robot that's actually successfully hopping and then eventually doing flips and all this kind of stuff?
Well, in the very early days, I needed some better engineering than I could do myself. And I hired Ben Brown we each had our way of contributing to the design, and we came up with a thing that could start to work. I had some stupid ideas about how the actuation system should work, and we sorted that out. It wasn't that hard to make it balance once you get the physical machine to be working well enough and have enough control over the degrees of freedom. And then we very quickly, we started out by having it floating on an inclined airtable. And then that only gave us like 6 foot of travel. So once it started working, we switched to a thing that could run around the room on another device. It's hard to explain these without you seeing them, but you probably know what I'm talking about, a planarizer. And then the next big step was to make it work in 3D, which that was really the scary part. With these simple things, people had inverted pendulums at the time for years, and they could control them by driving a cart back and forth. But could you make it work in 3 dimensions while it's bouncing and all that? And but it turned out, not to be that hard to do, at least at the level of performance we achieved at the time.
So, okay, you mentioned inverted pendulum, but can you explain how a hopping stick in 3D can balance itself?
Yeah,
So
sure.
what does the actuation look like?
The simple story is that there's 3 things going on. There's something making it bounce, and we had a system that was estimating how high the robot was off the ground, and using that, there's energy that can be in 3 places in a pogo stick. One is in the spring, one is in the altitude, and the other is in the velocity. And so when at the top of the hop, it's all in the height. And so you could just measure how high you're going and thereby have an idea of a lot about the cycle, and you could decide whether to put more energy in or less. So that's one element. Then there's a part that you decide where to put the foot. And if you think when you're landing on the ground with respect to the center of mass. So if you think of a pole vaulter, the key thing the pole vaulter has to do is get its body to the right place when the pole gets stuck. If they're too far forward, they kind of get thrown backwards. If they're too far back, they go, over. And what they need to do is get it so that they go mostly up to get over the thing. And, high jumpers is the same kind of thing. So there's a calculation about where to put the foot, and we did something, relatively simple. And then there's a third part to keep the body at an attitude that's upright. Because if it gets too far, you could hop and just keep rotating around. But if it gets too far, then you run out of motion of the joints at the hips. So you have to do that. And we did that by applying a torque between the legs and the body every time the foot's on the ground. You only can do it while the foot's on the ground. In the air, the physics don't work out.
How far does it have to tilt before it's too late to be able to balance itself? Or it's impossible to balance itself, correct itself?
Well, you're asking an interesting question because in those days, we didn't actually optimize things. And they probably could have gone much further than we did and then had higher performance. And we just kind of got, a sketch of a solution and worked on that. And then in years since, some people working for us, some people working for others, people came up with all kinds of equations or algorithms for how to do a better job, be able to go faster. One of my students worked on getting things to go faster. Another one worked on climbing over obstacles. Because when you're running, it's one on the open ground. It's one thing. If you're running like up a stair, you have to adjust where you are. Otherwise, things don't work out right. You land your foot on the edge of the step. So there's other degrees of freedom to control if you're getting to more realistic, practical situations.
I think it's really interesting to ask about the early days because believing in yourself, believing that there's something interesting here. And then you mentioned finding somebody else, Ben Brown. What's that like, finding other people with whom you can build this crazy idea and actually make it work?
Probably the smartest thing I ever did is to find the other people.
Yeah.
I mean, when I look at it now, I look at Boston Dynamics and all the really excellent engineering there, people who really make stuff work. I'm only the dreamer.
So when you talk about pogo stick robot or legged robots, whether it's quadrupeds or humanoid robots, did people doubt that this is possible? Did you experience a lot of people around you kind of?
I don't know if they doubted whether it was possible, but I think they thought it was a waste of time.
Oh, it's not even an interesting problem.
I think for a lot of people, people who were I think it's been both, though. Some people, I felt like they were saying, "Oh, why are you wasting your time on this stupid problem?" But then I've been at many things where people have told me it's been an inspiration to go out and attack these harder things, and I think it has turned out. I think legged locomotion has turned out to be a useful thing.
Did you ever have like doubt about bringing Atlas to life, for example, or with Big Dog, just every step of the way? Did you have doubt like what this is too hard of a problem?
I mean, at first I wasn't an enthusiast for the humanoids because, again, it goes back to saying what's the functionality, and the form wasn't as important as the functionality. And also, there's an aspect to humanoid robots that's all about the cosmetics, where there isn't really other functionality, and that kind of is off-putting for me. As a roboticist, I think the functionality really matters. So probably that's why I avoided humanoid robots to start with. But I'll tell you, now, after we started working on them, you could see that the connection and the impact with other people, whether they're lay people or even other technical people, there's a special thing that goes on. Even though most of the humanoid robots aren't that much like a person.
But we anthropomorphize and we see
That's
the
right.
humanity. But also, like with Spot, you can see not the humanity, but the whatever we find compelling about social interactions there in Spot as well.
I'll tell you, I go around giving talks and take Spot to a lot of them. And it's amazing. The media likes to say that they're terrifying and that people are afraid. And YouTube commenters like to say that it's frightening. But when you take a Spot out there, now maybe it's self-selecting, but you get a crowd of people who want to take pictures, want to pose for selfies, want to operate the robot, want to pet it, want to put clothes on it. It's amazing.
Yeah, I love Spot. So if we move around history a little bit, so you said, I think in the early days of Boston Dynamics that you quietly worked on making a running version of Aibo,
Yeah, yeah,
Sony's robot dog.
yeah.
It's just an interesting little tidbit of history for me. What what stands out to you in memory from that task? For people who don't know, that little dog robot moves slowly. How did that become Big Dog? What was involved there? What was the dance between how do we make this cute little dog versus a thing that can actually carry a lot of payload and move fast and stuff like that?
What the connection was is that at that point, Boston Dynamics was mostly a physics-based simulation company. So when I left MIT to start Boston Dynamics, there was a few years of overlap, but the concept wasn't to start a robot company. The concept was to use this dynamic simulation tool that we developed to do robotics for other things. But working with Sony, we got back into robotics by doing the Aibo runner. We made some tools for programming Curio, which was a humanoid this big that could do some dancing and other kinds of fun stuff. And I don't think it ever reached the market, even though they did show it. When I look back, I say that we got us back where we belonged.
Yeah. You rediscovered the soul of the company.
That's right.
And so from there, it was always about robots.
Yeah.
So you started Boston Dynamics in 1992.
Right.
What are some fond memories from the early days?
One of the robots that we built wasn't actually a robot. It was a surgical simulator, but it had force feedback, so it had all the techniques of robotics.
Mm-hmm.
And you look down into this mirror, it actually was, and it looked like you were looking down onto the body you were working on.
Mm-hmm.
Your hands were underneath the mirror, so they were where you were looking. And you had tools in your hands that were connected up to these force feedback devices made by another MIT spin-out, Sensible Technologies. So they made the force feedback device. We attached the tools and we wrote all the software and did all the graphics. So we had 3D computer graphics. It was in the old days this was in the late 90s, when you had a silicon graphics computer that was about this big.
Mm-hmm.
It was the heater in the office, basically.
Nice.
And we were doing surgical operations, anastomosis, which was stitching tubes together, tubes like blood vessels or other things in their body. And you could feel and you could see the tissues move, and it was really exciting. And the idea was to make a trainer to teach surgeons how to do stuff. We built a scoring system because we interviewed surgeons that told us, what you're supposed to do and what you're not supposed to do. You're not supposed to tear the tissue. You're not supposed to touch it in any place except for where you're trying to engage. There were a bunch of rules.
Mhm.
So we built this thing and took it to a trade show, a surgical trade show. And the surgeons were practically lined up. Well, we kept the score and we posted their scores like on a video game. And those guys are so competitive that they really, really loved doing it. And they would come around and they see someone's score was higher there, so they would come back. But we figured out shortly after that we thought surgeons were going to pay us to get trained on these things. And the surgeons thought we should pay them in order to, so they could teach us about the thing. And there was no money from the surgeons.
Yeah.
And we looked at it and thought, well, maybe we could sell it to hospitals that would train their surgeons. And then we said, well, at the time we were probably a 12-person company or maybe 15 people. I don't remember. There's no way we could go after a marketing activity. The company was all bootstrapped in those years. We never had investors until Google bought us, which was after 20 years. So we didn't have any resources to go after hospitals. So we at one day, Rob and I were looking at that, and we said we'd built another simulator for knee arthroscopy,
Mhm.
and we said this isn't going to work, and we killed it, and we moved on. And that was really a milestone in the company because we sort of understood who we were and what would work and what wouldn't, even though technically it was really a fascinating thing.
What was that meeting like? Were you just like sitting at a table? You know what?
Probably.
We're going to pivot completely. We're going to let go of this thing we put so much hard work into, and then go back to the thing
It
we
just
came from.
always felt right once we did it,
Just look at each other and said, let's build robots.
Yeah.